This is FP3 January 2007, question 5. Multiplicative group G of order 9 has distinct elements P and Q. That doesn't mean they're the only elements in there, but they are distinct, both of which of order 3. The group is commutative, that'll be important later. The identity element is E, and it's given that Q is not equal to P squared. So when in a group table we were doing P blob P, we're not allowed to have the answer Q. Then it says write down the elements for a proper subgroup of G. Now, sometimes the best way to tackle questions like this would be to try and draw out a group table, but an order 9 group table is pretty big, and for 2 marks, that's not what they're wanting us to do here. We don't want to be writing down 81 results to get 2 marks. Now, for these proper subgroups, and notice that proper word, we'll come back to that, a proper subgroup which does not contain Q, proper subgroup which does not contain P, then we've got to find the order of each of the elements PQ and PQ squared. And these are going to be results in this table. That might be something else, but that's what you get when you do P blob Q. PQ squared, justify your answers, then state the possible orders of proper subgroups of G. That'll be a nice easy mark when it comes. Find 2 proper, underline that word, proper subgroups of G which are distinct from those in part 1, simplifying the elements. Okay, let's do this question. So, let's write some notes to remind ourselves. So G is order 9, and P and Q are order 3. So one of the things that we know is that P cubed is going to equal E, and Q cubed is going to equal E. And we also know that P squared is not equal to Q. So, start with question 1. Now, we need to find a proper subgroup of G which doesn't contain Q. So, let's see whether we can create ourselves a simple one, nice little cyclic subgroup of order 3, because we know that P cubed equals E. So, the first obvious one is it'll have P squared, not Q, and E, which is P cubed. There we have a little subgroup. No other letters involved. When you blob P is going to get you P squared, P blob E is P, and P squared blob P squared would become P again, because that would be P to the power 4, P cubed is E, so you get E times P, and you're back to P again, so that one will work. Then we want an equivalent one with Q. Well, let's just do the same. Let's just do Q squared and E. And because Q cubed is E, and Q squared is going to get us Q to the power 4, which will take us back to Q again. That's another nice little closed subgroup. So, 2 fairly easy marks. Now, part 2 says find the order of each of the elements PQ and PQ squared, justifying your answers. So, best way to find the order of it, we have to make an assumption it's not going to be very high, so we're just going to multiply it up and wait until we get back to E again. So we'll start with PQ squared, see if its order is 2. It probably isn't, but let's find out what happens. So PQ squared, now you'd normally have to write this as PQ, but of course this is a commutative group, so we're allowed to rearrange the order of this, and we'll get P squared, Q squared. Well, we don't know anything about P squared and Q squared other than the fact that P squared is not equal to Q, so that's definitely not going to collapse down to E, so the order is not 2. Now let's see whether the order might be 3, so we'll get PQ cubed. Now again, because it's a commutative group, and only because it's a commutative group, we can write that like this. And now we do know the order of P is 3, order of Q is 3, so that will collapse down to E. So order of PQ equals 3. First part of that done. And now let's look at the order of PQ squared. Let's square it first to see whether it's 2. Now, because of the commutativity, we can write it like this. So p squared q to the 4. But we know that q cubed is e, so that's going to equal p squared q, because 3 of those will collapse down to e. Now, square that again, or cube that, we get p cubed and q to the 6. P cubed is e, q to the 6 is e squared, so all of this just becomes e again. So we now know that the order of p q squared is 3, just like the other one. Right, next part of this question is asking us to state the possible orders of proper subgroups of G. Now, remember, proper subgroup means not the identity and not the group as a whole, and orders of subgroups have to divide the order of the group as a whole by Lagrange's theorem. So that means that we're looking for factors of 9, not 1 and 9, so we're left with 3. Nice and easy mark there. Part 4 then is find 2, again, proper subgroups of G which are distinct from those in part 1, simplifying the elements. Now, that sounds like could be a pretty open-ended question, but don't forget that in part 2 we found ourselves 2 nice little cyclic subgroups there, and so by discovering that the order of PQ was 3, so if the order of PQ is 3, it means that PQ all squared and PQ all cubed equaling E form a subgroup. So we can just write down here PQ and P squared Q squared, and that's the first nice little cyclic subgroup. And then the second one, we'll go with this one, which is E again, then PQ squared and PQ squared all squared. But they did ask us to simplify these, so we're going to have a look and see whether we can simplify this one. That one's the simplest it's going to get. But PQ squared squared is equal to P squared Q to the 4, which is P squared Q, because Q cubed is E. So in fact, our subgroup in its properly simplified form is going to be P squared Q. Now, those of you of a curious disposition are probably wondering where the additional answer they gave in the mark scheme comes from. Because if you notice in the mark scheme, they give a subgroup of E and P squared Q and P squared Q squared. The question is, where does that actually come from? How do they get down to that? Now, it is in fact the same as one of these others, and we can demonstrate how that happens by showing that PQ squared, which is our element here, if we just multiply that by E, or P cubed, we can get P cubed Q squared. It's the same thing, because that's really E in the middle. And then that's equal to P to the 4th Q squared, which is equal to P squared Q all squared. And one of the reasons that they showed this, you don't have to do this, that was an acceptable answer in the back, or this one, is that this one shows it very clearly as in its cyclic form, where this is the generator, P squared Q, that's it squared, that'll be it cubed. So that's where the final answer came from. And that's the end of question 5.